All right, let's get started. So today we're very happy to have Peng here to give a talk. Peng is an assistant professor of computer science at Georgia Tech University. She did her PhD at Rutgers University. She did her PhD at Georgia Tech and her postdoc at Yale. And her work has been recognized by various awards, including an NSF Career Award, as well as a Fox Best Student Paper Award. And without further ado, I'll hand it to Peng.
Okay. Thank you for the nice introduction, and thank you for inviting me to give a talk here. Today, I'm going to talk about how to split a special class of Cayley graphs. And this is a joint work with Surya Gava. He is currently a lecturer at Kumbi. He was a PhD student at Rutgers. By the way, if you have any questions during the talk, please feel free to interrupt. Okay, here is the mathematical question. Suppose I have an n-directed graph G with vertex set V and edge set. I want to split the edge set E into two subsets, E1 and E2, such that the two edge-induced subgraphs G1 and G2 are similar. And I will explain what I mean by similar shortly. For simplicity, let's assume that graph G is connected. If it is connected, then I can work on each connected component separately. And also, today, let's assume graph G is unweighted. We could ask the same question for a weighted graph. Okay. When I say two graphs G1 and G2 are similar, I really want that the Laplacian matrices of G1 and G2 are similar, and they are both similar to half of the Laplacian matrix of the original graph G. And I will define what is Laplacian matrix. And also, I will use L sub G to denote the Laplacian matrix of graph G. Suppose graph G has n vertices, then this Laplacian matrix Lg is an n by n dimensional matrix. Okay, so in this n by n dimensional matrix Lg, each row and each column corresponds to a vertex in the graph G. You could define the Laplacian matrix as the diagonal degree matrix minus the adjacency matrix. Well, here I want to give you another definition. So first, I want to define the Laplacian matrix of a single edge between vertex I and vertex J. I call this matrix L sub Ig, and I define it to be the vector Ei minus Ej times its transpose. Ei and Ej are the elementary basis vector. So this vector Ei minus Ej, you have value 1 for the ith coordinate, and you have value -1 for the jth coordinate, and the zeros everywhere else. Now I have an n-dimensional vector x, and I look at the quadratic form of x and this edge Laplacian. I get xi minus xj then squared. Here xi is the ith coordinate of x, and xj is the jth coordinate of x. Okay, how should we think about this? Now imagine this edge between I and j is a spring with spring constant 1. And I nail down these two vertices on a line at positions xi and xj. Then this quadratic form equals twice of the energy of this spring. Okay. Next, I can define the Laplacian matrix for the whole graph G. I call it Lg. This is the sum of all the edge Laplacians over the edges in G. And again, I have this quadratic form of x and Lg. This is just the sum of xi minus xj squared over all the edges with endpoints ig. And if I think that every edge is a spring with spring constant 1, then this is twice. And I nail the vertices at positions xi's. then this is twice of the total energy of the spring. Okay, in particular, if I have a subset of vertices S and I take X to be the characteristic vector of this subset S, meaning that xi is 1 if vertex I is in S, and xi is 0 if vertex I is not in S. Then this quadratic form is the number of cat edges. And here a cat edge is an edge with one endpoint in S and the other endpoint not in S. Okay. I can also look at the eigenvalues of the Laplacian matrix LG. It also tells us some information about the matrix. The smallest eigenvalue of LG is always 0. Because if I take X to be the all-one vector, then in this quadratic form, the term here is 0. Every term is 0, so the sum is 0. And also the second smallest eigenvalue is non-zero if and only if the graph G is connected. Okay, what I really want is that the difference between the two Laplacian matrices for G1 and G2 is upper bounded by some small number times the Laplacian matrix of the original graph G, and the lower bounded by a negative of this matrix. This means that for any vector x, if I look at all these quadratic forms, then the quadratic form of x and this difference matrix is upper bounded by a small constant. By a small number, maybe not constant, by a small number times quadratic form of x and LG, and lower bounded by negative of this number. And in particular, if my x is the characteristic vector of some subset of vertices, then this means that the number of cat edges in G1 roughly equals the number of cat edges in G2. Okay, so since the sum of LG1 and LG2 equals the Laplacian LG, then this also implies that the Laplacian of LG1 and also the Laplacian LG2 is roughly half of the Laplacian LG. And in particular, if the graph G is a regular graph and also expander, meaning that all the eigenvalues of LG are equal up to constant factors, then both these two subgraphs are expanders. Okay, if we iteratively split this subgraph G1 and G2, then after some iterations, we will get very good sparse subgraphs of G, which are very good spectral approximations for G. Oh, yeah.
Well, the Laplacian of edges, when you write E1 minus EG, you suppose that we are in an Euclidean space, or?
Sorry, I mean LG1 minus LG2.
No.
Oh, sorry.
Laplacian on the edges IG.
Oh, this.
Yes. When you write E1 minus EG.
Mm-hmm.
So they are edges, right?
Yeah, this is for edge between vertex I and vertex J. Oh, sorry, vector. N-dimensional vector. Okay. It has 1 for the S entry and 0s everywhere else. Yeah, sorry for the notation. Yeah, sometimes people use E for edges. Okay. Yeah, let me show you some existing results. In 2015, Marcus, Spielman, and Srivastava showed that suppose for every edge between vertex I and vertex J in the graph G, the effective resistance between vertex I and vertex J is upper bounded by some number alpha. Then there exists a splitting of G into G1 and G2 such that the difference between the two Laplacian matrices is upper bounded by some constant times root alpha times the Laplacian of the original graph and the lower bounded by negative of this matrix. So here, the effective resistance is this quadratic between I and J is this quadratic form of EI minus EJ and the pseudo inverse of LG. Or you could think of the whole graph as an electrical network where each edge is a resistor with resistance 1. Then this number is really the effective resistance between vertex I and between I and J. Okay, let me show you some examples. If I have a complete graph, then all these effective resistance are equal. And also, if I have a hypercube, all these effective resistance are also equal. And also, if my graph G is a regular graph, and also it's an expander, meaning that all the eigenvalues of this pseudo inverse of LG are equal up to constant, then you can say that all these effective resistance are equal up to constant factors. And this is a graph such that the effective resistance differ a lot. I have two cliques, and I connect these two cliques by a single edge. The effective resistance between these two vertices is 1. Well, the effective resistance between any two vertices here or any two vertices here is actually small. So if I want to split the edges of this graph, no matter how I split the edges, at least one of G1 and G2 must be disconnected, meaning that the Laplacian of the subgraph has at least 2 zero eigenvalues. So if I look at the difference, I get the trivial bound 1 here. So this bound really depends on the maximum effective resistance. There is also a lower bound for the maximum effective resistance. We can lower bound this alpha by some constant over the average vertex degree. This is by, here I sum up all the effective resistance between any two endpoints of an edge. This is a scalar. So this scalar equals the trace of this scalar. And the trace of this scalar. And then I can put this vector here. So I get this. And since trace is a linear function, I can move this sum inside the trace. And the sum of these rank 1 matrices is the Laplacian LG. And the trace of LG times its pseudo inverse is the rank of this matrix. And since we assume that G is connected, so there is only 1 zero eigenvalue, the rank is the number of vertices minus 1. And I take average, so alpha is greater than the average of the sum, and I get that number. Okay. I want to point out that the result by Marcus, Spielmann, and Srivastava actually holds for more general settings for splitting more general rank 1 matrices instead of the rank 1 matrices for the edges. And their result proves the Cayley-Singer conjecture. Well, they only show that there exists a splitting. The currently best known algorithm for finding such a splitting has exponential time. And it's open whether one can find such a splitting in polynomial time, even for very special graphs. As I mentioned before, if I iteratively split these two subgraphs G1 and G2, after some iterations, I will get a good spectral specifiers for the original graph G. And in these specifiers, every edge has unit weight, and I call this unweighted specifiers. Well, if we allow reweighting the edges, there are actually polynomial time algorithms that can find very good weighted specifiers for graph G. Okay. Yeah.
Wait, sorry. Why does this work if you don't allow reweighting of the edges? Like if you repeatedly perform the splitting, then aren't you basically driving down?
Yeah, and actually you can show that the maximum effective resistance of G1 is not too large. It's some number related to alpha, and also the maximum effective resistance of G2 is also is some number related to alpha. And then you do the sort of the same splitting, and you get let's say G11, G12. You get the difference between the Laplacians of G11 and G12 upper bounded by I will say root alpha prime times LG1, and the alpha root alpha prime is close to root alpha.
Okay,
so it's not too large.
But your specifier is not just one of the two splits, or
you could do one of the two splits, or you could. Oh
then why
well.
aren't you losing
You choose the sparser one.
Sure. Yeah.
Yeah.
But sorry, I guess then why aren't you losing sort of the constant in the like you should lose a factor of half plus minus 0.1 in the way you defined it before in each of the Laplacian forms if you take either one of them, right?
Sorry, but for the factor half, you mean the number of edges?
Or no, I mean
I mean the error here.
Or what I understood is that if you can perform the split, so that if I look at any quadratic form with the Laplacian of G1 or the Laplacian of G2, it's the same as the quadratic form with respect to the Laplacian of the original graph up to a half.
Factor.
Yeah.
Oh, yeah.
So why are we not losing that factor of 2 or half?
Actually we lose. And
okay.
after several iterations, we will get 1/2 to the power of the iteration.
Okay.
But since it's a factor, and if we multiply the specifier by that factor, then we get a spectral. Yeah, the edge weight is not 1.
So you are allowed to up.
Yeah.
I guess the point is you are scaling all the edges the same way.
The same way.
Yeah.
Well, here you could use different weights for the edges.
Yeah. Okay.
Yeah, thanks for the question. Yeah. Okay, and this talk I want to show you how to split a special class of graphs in polynomial time. And the graphs we consider are circulant graphs, which is a special case of Cayley graphs. Which is Cayley graphs on Z. Okay, suppose I have a circulant graph. The vertices are the integers modulo n, and I will let's say to denote the set of these integers. And I use the generating set S, which is a subset of Z minus 0, to define the edges of the graphs. Here, for every vertex I and every element S in the generating set, I put an edge from vertex I to vertex M class S. And to make this graph undirected, I want that the generating set is symmetric, meaning that if an element in the generating set, then negative of this element is also in the generating set. And here, we think of everybody modulo n. Okay. And by the definition, a circular graph is a regular graph, and the vertex degree is the number of vertices in the generating set. And here are also some examples. A complete graph is a circular graph where the generating set is Z minus 0. And a cycle is a circular graph where the generating set only has 2 elements, 1 and negative 1. And also, Cayley graph is a special case of a circular graph. And since S is symmetric, we will write the elements in S as plus minus A1, plus minus A2 up to plus minus AK. And I want to point out that since circular graphs are very special, actually we will say that all the eigenvalues and the eigenvectors of the Laplacians of circular graphs have explicit form. And this is actually the K to find the splitting of the edges. Okay, we show that if all the generators, the elements in the generating sets, form an arithmetic progression, then we know how to split the circular graph into two subgraphs G1 and G2 in polynomial time, such that the difference between the Laplacians of G1 and G2 is upper bounded by some constant over root K times the Laplacian of the original graph and the lower bounded by negative of this matrix. Okay, recall that this circulant graph has vertex degree 2K. And the maximum effective resistance is at least some constant over K. So this number is at most square root of the maximum effective resistance. And this matches the result by Marcus, Spielman, and Srivastava. Moreover, we can show that this 1 over root K is the best possible bound for this, no matter what kind of split of edges we use. Okay, how do we split this graph? Actually, we will split the generating set S. We will split it into two symmetric subsets. Then we get two circulant subgraphs. Equivalently, we will split these K numbers, A1 up to AK. And today we will look at a special case where these numbers, A1 up to AK, are 1, 2 up to K. For a general arithmetical progression, we can always reduce to this special case. Okay. As I mentioned before, the eigenvalues and the eigenvectors of the Laplacian matrix of a circular graph has explicit forms. So first, the eigenvectors only depend on the number of vertices and is independent of the generating set. The eigenvalues also have nice forms. For j from 0, 1 up to n minus 1, the j's eigenvalue lambda j equals the sum of these cosine functions. This equals the sum of 1 minus cosine theta j over all the generators S in the generating set. And this theta j is 2 pi j over n, which is between 0 and 2 pi. Okay, since we assume the generators are plus minus 1, plus minus 2, up to plus minus k, then we can write the lambda j as 2 times the sum of 1 minus cosine S theta j over S from 1 to k. And here in particular, if j is 0, theta j is 0, and each term here is 0, so lambda j is 0, which is the trivial eigenvalue for a Laplacian. Okay, if we want to split the generating set into two symmetric sets, S1 and S2, then we get a circular graph G1 with generating set S1 and a circular graph G2 with generating set S2. Since all the graphs G1, G2, and G have n vertices, so the eigenvectors of the Laplacians LG1, LG2, and LG are the same. And since we want this bound, we only need to vary about the eigenvalues. And this significantly simplifies the algorithm. Okay, more specifically, we want to split this generating set S into two symmetric sets, S1 and S2, such that this inequality holds. Equivalently, we want for every j from 1 to n minus 1, the jth eigenvalue of LG1 minus LG2 is upper bounded by some constant over root k times the jth eigenvalue of LG, and the lower bounded by negative of this number. And here we drop j equals 0 because because everybody will have 0. Okay, further we can write the jth eigenvalue of the difference between these matrices as the difference between the jth eigenvalues of these two matrices. And we have explicit forms. The jth eigenvalue of LG1 is the sum of 1 minus cosine S theta j over S in the first set S1. And the jth eigenvalue of LG2 is the sum of 1 minus cosine S theta j over S in the second set S2. Okay, I can introduce an indicator xs for every generator S. xs is 1 if this generator S is in the first set S1, and xs is negative 1 if this S is in the second set S2. And then I can write this as 2 times the sum of xs times 1 minus cosine S theta j over S from 1 to k. Okay. This one also has the explicit form, which is 2 times the sum of 1 minus cosine S theta j over S from 1 to k. So this actually equals this number with every xs being 1. Okay, we can reformulate these inequalities in a matrix form. Here we define an n minus 1 times k dimensional matrix M, where each row corresponds to an index j from 1 to n minus 1, and each column corresponds to a generator. And the entry in the jth row and the s column is 1 minus cosine S theta j. And we also define an n minus 1 dimensional vector B, where the jth entry is the sum of 1 minus cosine S theta j over S from 1 to k, which is also the sum of the numbers in the jth row of this matrix. Okay, then our goal is to find a k-dimensional vector x with entries 1 or negative 1, such that for every j, the jth entry of mx, which equals this number, is upper bounded by some constant over root k times the jth entry OB, which equals this number, and the lower bounded by negative of this number. Okay. Let me start with a simple case where all the entries OB are sufficiently large. They're in the order of k. And here is a plot of the entries of B where n equals 1000 and k equals 4k. The x-axis corresponds to the index j, and the y-axis corresponds to the values of the entries of B. And we can say that all the entries of B are between 400 and 500. And also this happens when n and k are in the same order, so n is not too large compared to k. Okay, for this case, if we want this, then this is the same that we want every entry of mx has absolute value upper bounded by some constant times root k. Because every entry will be between some constant times k and 2k. Okay. Yeah, and this is our goal. And actually, it turns out we can get this vector x by directly using a result from discrepancy theory. And here we observe that the dimension of M is big O over k times k, since n is in n equals big O over k, and all the entries of this matrix are between 0 and 2. So Spence, there is a famous result in discrepancy theory called Spencer's theorem, which actually gives the answer to this question. So it says that suppose we are given a matrix M in n by k dimensions, where each entry are bounded. For example, here each entry are between 0 and 2. Then there exists a k-dimensional vector x such that every entry of mx has absolute value upper bounded by root k times root log n over k. And later, people showed that we can find such a vector x in polynomial type. And in this case, our n is big O over k. So this log factor is a constant. And we get root k for for every entry of mx. Well, in general, the entries of B could be both large and small. So here is a plot for the entries of B when n equals 1000 and k equals 40. And we can say that when j is close to 0 or close to n, the entries of B are very close to 0. And this j being close to 0 or close to n corresponds to theta j being very close to 0 or 2 pi. And we need to handle both these two cases. And here we handle these two cases separately. Again, for the large entries bj, we want that the absolute value of the jth entry of mx is upper bounded by some constant times root k. Well, we can't directly apply Spencer's theorem here, because now our n could be much larger than k, and this log factor is no longer a constant. If we directly apply this, then we get some bound which could be much larger than root k. Well, actually, it turns out the cosine functions are very nice. And in the same paper by Spencer, he actually also answered this question for such a special matrix M. So here we look at this function f sub x of theta, which is the sum of xs times 1 minus cosine s theta over s from 1 to k. It turns out this function does not fluctuate too much if k is small. And we only need to look at about 9k evenly spaced numbers for theta from 0 to 2 pi. And if we can show that for these about 9k numbers, we have this bound, then we have this bound for everybody from 0 to 2 pi. So, which means that we could remove a lot of rows from this matrix M, and we get a smaller matrix which only have
9k rows and k columns, and we can apply Spencer's result again. For this small interest bj, we want this ratio to be at most, or the absolute value of this ratio to be at most some constant over root k. And by symmetry, okay, as we said before, the small interest bj corresponds to the theta j either very close to 0 or very close to 2 pi. And here, by the symmetry of the cosine function, we only need to look at the theta j, which is very close to 0. And here we take the Taylor expansion of cosine of this cosine function. And here, actually, we need about log k terms in the Taylor expansion. Okay, so we got this, and this theta is not too large, so we can put this inside this sum. And we got this. Now this right-hand side is independent of theta. And we want that for each sum here, for a particular L, we want this sum is upper bounded by log k. And we have log k terms here, so the whole thing is upper bounded by log k squared. And then we have k inverse here. So the first term will be upper bounded by log k squared over k, which is much smaller than 1 over root k. And the second term is little o of k to the power negative 3, which is also much smaller than 1 over root k. Okay, so in summary, we want a k-dimensional vector x with entries 1 or negative 1, such that the following two conditions hold. The first condition corresponds to the large entries of the large entries of B, and the second corresponds to the small entries of B. And the first one has about 9k equations here, and the second one has about log k equations here. And we can find such a vector x by a modification of Spencer's theorem. Okay. We also show some lower bound for splitting the generating set. We show that if these generators are far from an arithmetical progression, then there is no split of the generating set S into two symmetric sets, S1 and S2, such that we match the Marcus-Spielmann and the Srivastava bound. Maybe more specifically, we show that there exists a universal constant C such that for sufficiently large K and N, if all these generators have increasingly large gaps, then there is no splitting, such that the two subgraphs satisfy LG1 minus LG2, upper bounded by C times root alpha times root log K times the Laplacian of the original graph, and the lower bounded by negative of this matrix. Here, alpha is the maximum effective resistance. Yeah.
So what you're saying here is just by splitting the generators, it's not enough to get algorithmic Huntington-Singer on this graph. You have to split the edges
yes.
of
yes.
a particular generator.
And we show this proof by, we show this theorem by two theorems. So first, we replaced this bound by C times root log K over K. So there is no alpha here. And second, we show that the alpha is not too large. the alpha is roughly 1 over k. And then combining these two results, we will get this lower bound. We will get, sorry, maybe not the lower bound. We will get this bound. Okay. Yeah, I will show you some proof ideas of this theorem, and I call it a theorem prime. We will prove it by contradiction. We assume there exists a split of the generating set S into S1 and S2 such that this bound holds. And this is the same as we assume there exists this signs x1 up to xk such that the maximum absolute value of this ratio is upper bounded by this number. And here the maximum is taken over all the theta being 2 pi j over n for j from 1 to n minus 1. Okay, we observe the denominator is always upper bounded by 2k. And then this assumption implies there exists the signs x1 up to x1 up to xk such that the maximum absolute value of the numerator is upper bounded by 2c times root k times log k. We multiply this 2k here. And this is the same. Sorry. I just moved this to here. Okay, so we want to further simplify this sum. We split this sum as the sum of xi's minus the sum of xi times cosine alpha I theta. And since we assume this, the two Laplacians of g1 and g2 are close to each other, this implies the sum of xi's cannot be too far from 0. The sum of xi's corresponds to the difference between the vertex degree of the two subgraphs. And if we want to get a contradiction, it suffices to show that this number has a large absolute value. So our goal becomes to show for any signs x1 up to sk, there always exists a theta such that the absolute value of this number is greater than 4c times root k times root log k. Then the absolute value of this number is greater than 4c times root k root log k minus c times root k root log k, which is greater than 2c times root k root log k. So our goal becomes to lower bound this. And for sufficiently large n, we could approximate this number by the maximum absolute value of the sum. Well, now the maximum is taken over theta from 0 to 2 pi. Yeah, it turns out this sum actually is well studied if this A1 up to AK have increasingly large gaps. And this sum is called the Laquinary trigonometric series. And people have studied that if this theta is sampled uniformly at random from this interval, then the limiting distribution of this sum, actually, as k goes to infinity, actually the limiting distribution is a Gaussian distribution. And well, this is not enough for our proof. We show that when theta is drawn uniformly at random from this interval, then with probability roughly 1 over k, we have the absolute value of this sum greater than 4c times root k root log k. Okay, we also have some results on algorithms for like generalizations of arithmetic progression generators. So here, if we allow some small perturbations for each generator, then we can get the same bound. And also, if we look at higher dimensional circulant graphs, which are Cartesian products of circulant graphs with arithmetic progression generators, we can also get similar bounds. Okay, I think this is all for the talk, and thank you all very much. And I'm happy to answer any questions.
Yeah, sorry. So I guess I have kind of like a general question. So like, even if we do obtain efficient like polytime splittings of graphs that satisfy the properties that you're interested in here, are there new results implied? What other? Because I guess we know how to efficiently construct spectral sparsifiers.
Mm-hmm.
So we don't necessarily need this for spectral sparsifiers. So what do you get? I guess sort of the dream came true here.
Yeah. So if we think an expander as a spectral specifier of the complete graph, then we know how to construct an expander. Well, if our graph is not a complete graph, maybe an arbitrary graph, we want to construct a unweighted specifier, then we do not know how to do it. Okay. And maybe if you have an algorithm for this, then you can use it iteratively and get a good unweighted specifier for any graph. Okay. I mean, a graph with small maximum effective resistance.
Right. But which is not an expander.
Yeah, it may be not an expander. It depends on the original graph. Yeah.
Yeah, I also have a few general questions. So I was wondering, what's the motivation for the graph splitting, or like why people are interested in this problem in general? And also, I see that this definition makes sense, like approximating this Laplacian matrix of a graph. But are there other definitions that you can consider, or why are people, or is this the only definition that people have looked at?
Oh, I think there are like many different definitions for graph specifiers. So people might be, they might want to preserve some other, let's say, numbers of the graphs. There are cat specifiers. You want to preserve the cats of the graph. And there might also be results that people want to preserve some flow, right, and some other.
Yeah, I can
thing.
understand like graph specifier, but the like graph splitting is different, right? I want to split into two graphs, and both are like a good approximation of the original graph.
Mm-hmm.
Like, why are people particularly interested in this problem, or it's just interesting?
Yeah, I see the question. So I think first you can use this as a subroutine for getting graph specifier, and second, actually the technique used in the Marcus-Spielmann and Srivastava results, they have many other applications. And the question is whether you can make all these applications algorithmic. Well, this is a very special case because the general question is very hard. Well, maybe there is some hope to tackle the general question by starting with the special one.
Yeah, I don't know the significance of Cartesian singular either, other than it won Nevelina Prize. My understanding is that a lot of the Cartesian singular conjecture showed up in various forms in a lot of different areas in mathematics, and even the existence of such partition was open for 50 years or something. And I remember sitting at Stalfox talks, hearing people say that if Cartesian singular can be algorithmic, then we can do something, but we cannot, and therefore, here's my paper. But these are, I don't know if you have a problem that you don't know whether it's in P or not, and then suddenly given algorithmic Cartesian singular, you can put it in P. I don't actually know. Maybe someone should write a survey on significance of Cartesian singular.
I think Nick Harvey has a pretty good survey on it.
I see.
Uh-huh.
Right. I just have one quick question on the relationship between discrepancy and Cartesian singular. Is that something that people have? Your work is one example of such things, because it feels like you're trying to do the same thing, right? Like you're trying to come up with plus minus one sign, so that my understanding of discrepancy is you are trying to beat union bound, right? You don't want to pay this
and also this one, you also try to beat the random splitting.
Right.
Yeah, if you do the random splitting, then you will get root alpha times a root log factor.
Right, and that root log is all I'm trying to get rid of here, right?
Yes.
Yeah. Right. Because there are open problems in discrepancy as well, right? Right. Like, are there any other examples that, like maybe it's the same thing, or like how closely related is discrepancy to algorithmic Cartesian?
I think if you define discrepancy very generally, so here you want to minimize the discrepancy of your splitting, because you want the difference between LG1 and LG2, roughly equals 0.
Right.
Yeah.
All right, let's thank the speaker again.